Hello, everyone, and thank you for joining us today for this webinar series, Digital Hydroconnectivity. This 5-part series will continue each week at this time through the end of the month. This is the 3rd talk in the series, and all of these talks will be recorded and posted on the CUAHSI YouTube channel. If you're interested in reviewing some of the previous ones, you can view those on the YouTube channel later as well. My name is Julia Masterman. I'm the Science Education and Outreach Specialist for CUAHSI. CUAHSI is a consortium of universities for the advancement of hydrologic science, and our mission is to advance water science by strengthening interdisciplinary collaboration, empowering the community by providing critical infrastructure, and promoting education in water science at all levels, in part through programs like this Cyberseminar Series. We seek to achieve this mission through our community services and our data services. Very briefly, some things to note about our community services. We are accepting training workshop proposals right now. If there's a specialized topic or method that you'd like to share with the water science community, CUAHSI may be able to help host a workshop for that. If you're interested in that, you can find more information on our website. We also have proposals open for a number of funding opportunities, including our Hydroinformatics Innovation Fellowship. This is a really unique fellowship. Examples of previous projects that have been completed through this fellowship can be found on the CUAHSI website, and the application deadline is coming up soon. So if that's of interest, please take a moment to check that out. The other side of our house, so to speak, are our data services, and CUAHSI data services include tools and support to enable all parts of the data lifecycle. A couple highlights include our 2 data repositories, HydroShare and HydroClient. It's very brief, so I'd encourage you to get in touch and join the CUAHSI community, either on Slack, follow us on Twitter, or sign up for our newsletter. Feel free to reach out to me as well. My email is up there. But with that, thank you for joining this webinar series today. Before I introduce our speaker today and hand it off to the convener, a few logistics. This webinar is being recorded and will be posted on the CUAHSI YouTube channel later this afternoon. Secondly, we ask that you use the Q&A functionality to submit questions to our panelists rather than the chat. And finally, we expect that all involved with CUAHSI Cyberseminars promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you for being a part of that. Thank you again for joining us, and especially to our speaker today, Dr. David Blodgett, for joining us, as well as our convener, Sudarshana Mukhopadhyay, for convening the speakers in this series. With that, I'll pass it off to our speaker and convener for our talk, Maintaining Rivers and Persistent Hydrographic Addressing the Context of Linked Open Data.
Thank you.
Thanks. Bye.
Thank you, Julia. Once again, thank you all for joining us today. I'm very excited about our talk today. And as Julia mentioned, we'll be monitoring the Q&A section on Zoom throughout the presentation, and we'll save the questions for the end. So today's speaker is David Blodgett from USGS. He is currently working as a hydroinformatics lead across the USGS water mission area and the hydroscience community. So without further ado, let's start the presentation. I'll turn it over to you, David.
Excellent. Can you hear me okay?
Yep.
Great. All right. Well, thank you. And Julia, I'm not a doctor. I'm just a civil engineer with a data habit. It's been about 10, 12 years now with the US Geological Survey after getting a master's at the University of Wisconsin-Madison in environmental fluid mechanics. And since I've been with the GS, I've been working on various activities around large and diverse geospatial data, really focused on environmental modeling, water resources modeling, water budgets, these kinds of things. So I'm in the USGS water mission area, which is a headquarters part of USGS. USGS is distributed across the landscape in a collection of science centers. And then there's a number of headquarters offices, and I'm in the water mission area, which has some structure to it, as any kind of big organization like this does. And the part of the organization I sit in is called the Integrated Modeling and Prediction Division. And the specific branch is a geospatial intelligence branch. So we do work on kind of data standards, techniques, algorithm development, systems development, and kind of working across the USGS and kind of broader academic and practitioner community to advance geospatial intelligence for water resources. So with that, I'm going to jump in to my slides, talking about the Mainstems data model here. This is some work I've completed in the last year or two. It's been in the works for quite some time. That's largely built off of the NHDPlus, but is kind of taking the next step to kind of break out of the traditional geodatabase construct for hydrographic data and put it into the context of linked open data. So a little bit of background that I think is just really important to recognize the kind of the academic space that we sit in. And I like this progression, and I like to kind of make the point that if we're talking about going beyond machine learning, which is really correlation based kind of advanced statistical inference, we need better representation of semantics. And so there's a whole research agenda built up around this that's fairly well thought out, that kind of points to the need for more nuanced tracking of knowledge and semantics, and that's what this Mainstems work aims to do. And it's aiming to take the semantics that are typically wrapped up in these geodata models, such as the NHDPlus, and kind of break out of that and turn it into something that can be accessed in a more kind of integrative, open, distributed way. So given that kind of really high level background and context, what do we need in that context for quote unquote digital hydroconnectivity, which is what we're here to talk about. And I pulled this sentence out of the manuscript, the Mainstems manuscript, which you should have a link to in the chat, I believe, or will soon. Yeah, you do. You should soon. Julia was going to share it to everybody. So by defining mainstem flow paths and identifying them across data sets, the sophistication of incremental catchment data models can be handled simultaneously with a persistent and minimal network of mainstem flow paths connecting headwater and outlet locations. So this is really the gist of the whole talk. I'm done. We can all go have lunch. But seriously, what we're talking about here is identification of these aggregate flow path collections that we call a mainstem, identifying that collection in a way that we can find it in multiple data sets, and then trying to persist that identified collection and how it's identified in a way that consistently connects headwaters to outlets. And if we can consistently connect a headwater location to an outlet in a watershed and have a reasonable identifier for the path that connects those two places, we have a way to, at least using a hydrologic lens, unify these data sets. So let's go back in time to the very beginning. And so I did a fairly deep search of the literature for where some of these ideas originated, and how early we can go back and find these concepts of drainage basin and mainstem. And I love this graphic. So this is actually from the 17th century, in a study on quantitative hydrology, where we have a basin boundary for the Seine River upstream of Paris and labeled mainstems going up to Source Seine, which is actually a town. that's named for the source of the Seine. So this is the headwater area of the Seine River. And so, I mean, these ideas of a polygon that surrounds a drainage basin that has one main stem that goes to some source area, these ideas are really old. And what this has led me to think about, and one of my co-authors, Mike Johnson, he wrote some of the more compelling language around this, is these concepts of drainage basin and main stem may be too intuitive or too deeply ingrained in our kind of casual discourse to be especially useful for precise scientific or knowledge management purposes, right? So, when we get too casual with our language, obviously it's easy to make assumptions, and we don't want to make assumptions when we're tracking very specific concepts and things that need to be handled for, say, scientific reproducibility. So that sent me down this rabbit hole of where's a tight definition of the idea of a drainage basin? Where is that, or a watershed, right? And so this book, The Fluvial Hydrosystems, which is actually kind of more of an ecological perspective on fluvial systems, provides this really nice definition where a drainage basin is described as a cascading system of connected hill slope and channel subsystems. And this idea of a cascading system of hill slope and channel subsystems, that's a drainage basin made up of catchments that connect in an upstream and downstream direction. A hill slope and channel subsystem, that's a catchment. The cascading system is a drainage basin. And this drainage basin terminology it's fairly consistent. The watershed term is not used consistently in the literature. It's used variously for lots of different purposes. It's very vague. I tend to avoid using the term watershed now because while it does have meaning in a general sense, it does not have a precise definition that I've been able to really nail down. And this idea of a drainage basin does in practice have a much tighter notion of a complete watershed that drains to one location. So coming back to, this is a sentence straight out of the report, the Mainstems report. The intuitive properties of these landscape mechanics have resulted in a general vagueness about how hydrologic features are described, referenced, and in some cases understood. So this is the problem, right? This is when people complain about hydrologic science not being reproducible, this is one of the core issues that we have. So just keying in on a few important things here. This central thing, rivers have a drainage basin upstream of a given location, is super duper key. And this integration of rivers as the drainage system for a drainage basin is really what we end up exploring in hydroscience, and what this Mainstems data model is attempting to formalize. Okay, so moving to the kind of linked data context. We have these four functions in digital hydroconnectivity. We have persistence, discovery, integration, and access. Now, some of you are familiar with the Internet of Water. This is this kind of big pan community project to elevate the availability of water data kind of across the board. And in that space, we've been working on a system called geoconnects.us. Type geoconnects.us into your browser and you'll find it. And we're in that space, we're attempting to create something of a resolver, like the digital object identifier resolver, for environmental features, monitoring various data that might be associated with those kinds of things, modeling, et cetera. And that's an attempt to provide a space where we can have persistence of identifiers and redirection to the data about those identified entities. So then coming over to discovery, there's systems like the Network Linked Data Index. This is something I've been working on kind of in the context of this Mainstems work for a few years. That's intended to be a search engine over the network of catchments and flow lines and flow paths that make up the NHDPlus, and longer term, any network, The long-term vision here is that this provides a utility to do network navigation and discovery of linked content, potentially, probably globally. So then integration, environmental and monitoring features, right? We need to consistently, carefully, without undue duplication, catalog and integrate the environmental features, the both built and natural environment, and the features that we use to monitor the environment, right? That all needs to be in some way organized and connected together, both digitally and in the real world. And those two representations, the digital representation of our system of environmental monitoring needs to be fairly rich and fairly robust if we're going to achieve some of the goals that we have. And then access, right? Everything has a representation, whether it's an observational time series or a polygon that represents the boundary of a watershed, right? We need to be able to access these data. And that access is ultimately probably the point. It's not, all this other stuff is just very meta. But if you don't have all the meta, you can't get to the point. So digging into some detail, there's a couple projects that were done leading up to kind of the state of play that we have with geoconnects.us and some of the network linked data index work. One called ELFI, the other called SELFI. This stands for the Environmental Linked Features Interoperability Experiment, and the second Environmental Linked Features Interoperability Experiment. And so the graphic I have on the screen is from the first. So when thinking about an environmental feature, a river, right? When you go to Wikipedia and look up a river, or you go to Google and look up a river and you get a Wikipedia page, there's the way we thought about this in the ELFI project was there's kind of two perspectives on that feature that have a distinct role in how we discover information and catalog information about a feature. So one role is this idea of a preview, right? Just let me know what it is, where it is, what it looks like, basic information about it, right? The other is, how does it relate to the rest of the world? This idea of a network. And so these are two kind of functionally defined views of the graph, the knowledge graph that we might catalog about an environmental feature. And we really could do this for any environmental feature or monitoring feature or anything really. Tell me what it is, tell me where it is, and then tell me how it relates to the things around it. And the network view could have a much richer set of associations than is shown in this graphic. This graphic is really just about spatial and temporal topology, or how things connect to each other in space and time. This could include relationships from other or more specific scientific domains, water resources, geology, geography, specific nuanced associations between features that are defined in a specific kind of scientific domain knowledge system. Okay, so that's some background. This is just some high-level background on Mainstems and kind of where we are, or what we've been working on in the community on the kind of environmental linked features, linked open data space. Now let's dig into the content a little bit more and think about this in a more applied way. So I have on the screen the new NWIS monitoring location page for the Rio Grande and Budo, New Mexico, and the map screenshot here is actually available, scrolled down a little bit below the time series plot. So we've got a monitoring location, the blue pin. We have an upstream flow line, which is actually the main stem of the Rio Grande in this context. We have a downstream flow line, which is the main stem downstream of this location, and we have an upstream basin. We all pretty much get this, but it's not super duper trivial. I mean, this is what you're looking at here is a union of all the NHDPlus version 2 catchments that are in the upstream with tributaries graph of flow lines from this monitoring location, which has been indexed to a particular location on the collection of NHDPlus version 2 flow lines. This path, this upstream mainstem path, was chosen very carefully with an algorithm to choose how to follow named features versus unnamed features versus small rivers versus big rivers, et cetera, right. There's a lot of nuance that's tied up in this graphic and in what's going on here. And it all comes down to this idea that this region of the landscape can create an output that is a flow, right? It's this basin has a real landscape function that we all study, right? And we're trying to, it's very general, it's very abstract, but ultimately we're trying to track that association between some region of the landscape and its outlet location. And we're trying to do it in a systematic way because, by the way, every one of the red dots on this map could have this same association to the landscape in a different way. And there's a lot more than just the red dots you see here. There's anywhere on the landscape we could monitor or model this phenomena or these sets of phenomena that occur in the kind of landscape connection. Okay, so to do that in a precise way, we need to decompose this problem, and we need to do a little bit of informatics and hydroinformatics in this context. And so for hydroinformatics, we tend to decompose for most spatial informatics problems. We tend to decompose the problem in two ways: using some kind of spatial domain decomposition, which in our context in water science is often for kind of social or engineering reasons, right? We choose our watershed outlets carefully based on what we want to study related to societal or engineering purposes, right? If you're gonna size a culvert, you have chosen a watershed for engineering reasons. If you're going to try to understand water availability and supply for agriculture, you've done it for social reasons. And you've decomposed a spatial domain for those reasons, right? The other way we do it is by model concept domain, which is decomposition of a problem into components that can be solved using kind of independent methodologies, right? Or decoupled methodologies that can be coupled maybe if you need to, but don't even necessarily have to be. So you might solve a soil water balance separate from the runoff process, right? And you might couple them up as needed, but they really can be run as two separate processes that just meet at their seams. And so we do that all the time, right? Hydrodynamic modeling gets done separate from hydrologic runoff modeling. And so that model concept domain decomposition is kind of done all over the place. So that's one important way that we solve these problems, right? We break them down in different ways. So that's one kind of piece of the formalism that we're using here and thinking about carefully. The second piece that folks might not be familiar with is this idea of formalizing entities, in this case, spatial features, with the idea of class. So, and this is a computer science type class, right? So this is a set or category of things having some property or attribute in common and differentiated from others by kind, type, or quality, right? And in object-oriented computer science, this takes on a certain meaning. What we're talking about here is more in information modeling. A class is a thing that can have a type, and it can have a bunch of attributes. It can have associations to other things, and it basically defines a concept in a very formal and rigorous way. So we've done that for surface hydrology features in a data model called HY features. And so this is something that was published through the Open Geospatial Consortium and defines fairly rigorously these core components of hydrologic systems. And so this pictogram I have here is what I'm going to step through now, that talks about how we break down these concepts. So the first is this idea of a catchment area. This is not inclusive of the boundary. I'll be very careful. The catchment area is the stuff inside the boundary, which is subtle, but it's important. So this area is the thing that, if in a digital representation, calculates the water budget. In a physical representation, actually, the water budget happens in the catchment area. It happens over the catchment area. The catchment area delivers flow to a drainage network, right? There's going to be some network of rivers in this green area that receives the runoff component of the water budget that's happening in that area. And how this catchment area is realized digitally is totally flexible, right? In a modeling context, this could be a mesh of triangular elements. This could be a raster. This could be a continuous parameter estimate across the whole area. There's a lot of different ways that we might model or represent a catchment area. So the next one is flow path. A flow path is just a linear connection from a catchment inlet to an outlet. A flow path can connect to a water body. The connections between water bodies and flow paths would typically be between things we call hydrolocations. So that gets into kind of linear referencing. The flow path is really the thing we use to express upstream, downstream topology or ordering, right? We need some one-dimensional representation of flowing water so that we can express this idea of linear connectivity, right? It's hard to do linear connectivity on 2D, 3D objects. It's not impossible, but you generally you have to linearize your element if you're going to get a distinct top to bottom ordering, right? And this flow path idea might support hydrologic routing, but in you would not think about a hydrodynamic model being appropriate on a flow path, on a 1D representation. You would almost always jump out and have some other channel water body kind of representation that could couple to these flow paths via hydrolocations. But typically this flow path concept is not associated with hydrodynamics. So that gets us to water bodies. And there's, I don't go into it here, but there's a partner class in high features for channels, essentially. So there's a wet part and a dry part. You might have a channel that has geometry. You might have a water body that has, properties like depth. The channel doesn't have a property of depth. The water body does. So a water body is an aggregation of, a water body is a thing like a river, lake, or an impoundment. And it's an aggregation of water bodies can be identified actually as a realization of a catchment. And this is an interesting, so I think if we go back, did I make this point? I guess I didn't really dig into it yet. So a catchment is, when I was talking about the catchment area, I said that the catchment area is distinct from the boundary and it has a particular role. The catchment is it's a holistic concept that we decompose, right? We decompose the idea of a catchment into a thing that can calculate a water budget, a thing that has a boundary, and everything inside that boundary contributes to an outlet. The catchment has a main stem river. The catchment has a network of rivers that kind of represent some functional perspective of this idea of a holistic feature that is a catchment, right? And so the high features data model represents catchments in that way. It says, look, there's this high level thing that is a catchment that can associate in an upstream and downstream direction to other catchments through some kind of joining feature that we call a hydronexus. And a catchment can be realized in various ways, right, for various purposes. And that's necessary. And that allows us to kind of step back from these problems, getting to the kind of decomposition we decompose the catchment into multiple representations that can be used to solve different kinds of problems. So another feature that's really important to recognize here is the lowly hydrolocation, which I've got represented as a dot. That's not a dirty screen, it's just a dot. A hydrolocation is a location along a flow path that we use to link to other things. And it becomes kind of the most valuable feature in any data set because it's the thing that actually relates your data set to the rest of the world. So gauges, cross sections that link to water bodies, reporting locations in your model, nexus locations in other data sets, right? Say you have a model that has however many watersheds represented and you want to link that to the NHDPlus network, right? You would represent the confluences, the nexus locations in the NHDPlus as hydrolocations in your model. Okay, so I've worked up this little pictogram representation that I like to come back to this every once in a while just to kind of remind myself how core these concepts are. But this idea that there's a holistic thing called a catchment that connects to the rest of the world via nexuses. Hydrolocations can be the link to connect a nexus to a particular flow path in a particular data set. We've got water bodies, they link to flow paths, and we create infinitely complex systems of these core features, these base features. The complexity that you can create using this basic logic is pretty bonkers. And some of the models that are out there are evidence of that. Okay, so I'm at 30. We're doing good on time. I've got two slides here of UML diagrams. So these are class models. So going back to the terminology of class, each of the boxes in this diagram is a class. It has a type. It has a stereotype. The feature type thing here is actually like the type of the type. But don't pay too much attention to that. It has a name. It has some associations. It has some attributes. So these red description, or these red pieces are attributes that these classes would be expected to have. It might have constraints. The constraints could be expressed as attributes. Typically, that's how that would be done. But they're special sorts of attributes that relate to the role of the class in the rest of the kind of model. And so what we're looking at right now is the nexus and catchment classes and how they relate in this system via inflow, outflow, contributing, receiving kind of relationships. And then this bottom little diagram is how the hydrolocation feature relates to a hydronexus. And the hydrolocation has an indirect position, which has some constraints. The indirect position has a point referent, which is kind of the point that it's relative to, and it's measured along a flow path. So if you're familiar with reach codes and measures in NHDPlus, the reach code and measure data model is an instance of this indirect position model. And the hydrolocation is, say, the stream gauge that the event is locating on the network, right? Or whatever thing is being located along the network. It has an indirect position that is expressed as an event feature. And so in HY features parlance, that's an indirect position. So this association from a hydrolocation to a nexus is basically to say that any location can be thought of as a nexus. We don't have to, but any location on the network is an outlet of some watershed, of some basin, right? Conceptually, anyways, whether we create that actual outlet feature or not, it is a nexus and could have a nexus identified, which would then take part in a network of catchments, or could take part in a network of catchments. Okay, so the diagram here on the upper right is this catchment realization concept that I was talking about a second ago. We have our catchment, this high level identified kind of unit of hydrology. It has realization. There are multiple classes of realization. So this open arrow implies a subclass relationship, right? So we have a cartographic realization. We might have a map of the catchment. We have a divide realization. We could have a polygon that is encompassing a catchment. We could have a flow path representation. So this is the line that connects its inflow to its outflow. Or we could have an area, which could be some attribute space that represents the characteristics that are enclosed by the divide, right? And there's another subclass of catchment realization that is network. And this is where we get kind of cross-scale networks of catchments that nest within each other. Because this hydro network, note that a hydro network can be a system of flow paths, catchment areas, or catchment divides. But it's still a subclass of catchment realization. So there's an implied kind of nesting relationship here between these realizations that can form networks. So given all of that, which is hopefully this is giving you a high level overview of this stuff. Don't pretend you're going to take it all in right now. It's giving you some touch points to come back to later. There's another, so now I'm adding, actually not adding a lot of information, but I am adding information about indirect positions and how the indirect position might relate to a flow path, because this is really the key to persistent linear referencing, which is what I'm hoping to get to in this talk, where we have a flow path, which is the linear element that we're measuring our indirect position along. So this flow path needs to be persistent if your indirect position data is going to be persistent. We need to have a stable we need to have a stable ruler with which to measure our locations along a river network. And that's a tricky proposition. That's a tricky problem. If we were to automate the creation of these indirect positions, the question becomes, what information do we need to consistently, reproducibly automate generation of these indirect positions so that we then have an upstream, downstream kind of ordering of things that are along rivers, which is kind of the core need here, right? And if we so jumping all the way to the end, if we boil it all the way down, all we really need is what main stem river is the hydrolocation to be associated with. So if the one thing that gets recorded in our indirect position is the measure along flow path, and that where that flow path is just a main stem river, that gets us 90% of the way there. And the reason it gets us 90% of the way there is that the really hard problem when it comes to finding indirect positions of generic hydrolocations is, am I on a tributary or am I on the main stem? Because especially in very high resolution hydrographic data, there's always a tributary closer, it seems like anyways, there's always some tributary closer to your gauge house or your gauge point of interest than the flow line for the main stem that the thing is actually on. Like invariably, there's always some piddly little line that you auto snap to instead of the one that you should have snapped to. And you need that kind of positive assertion of I am on that river. And that's really what we want to zoom into, is this measure along flow path. What flow path am I on? The rest of this, the distance from a point referent, so the distance from the outlet of the next downstream kind of confluence maybe, that stuff can be generated on the fly, can be automated based on the data that we have today or the data that we're going to have tomorrow. As long as we know which flow path to start from or which flow path to attach to. So, in the conceptual data model, there's a lot more here. So just pointing out, like, we've got different ways of doing distance description. So it might be an absolute, like a meters. It might be interpolative, like a percent along. We might have a distance description that describes more detail about where relative to the point referent an indirect position is meant to be. Then there's also this idea of there's a lot of different hydrolocation types. And this list could grow. So like if your project had a whole bunch of data associated with the river network, you might pick from this list, you might extend this list and say, hey, I have hydrolocations of some type. And that allows the person from a knowledge management point of view to make a lot of assumptions about what they're dealing with that are really powerful. Okay, so we've dove way down into some details that I'm sure were more than a lot of you wanted to chew on. But hopefully that was at least halfway useful for some subset of the audience. If you want to dig in more on this Mainstems data model, I encourage you to check out the Mainstems paper. Looks like I'm seeing a link did not resolve. We'll fix that in the question and answer. Apologies. This Mainstems paper was it was a lot of work. Hopefully it's useful. It's fairly dense, but has a lot of examples and kind of digs into these details and these concepts pretty carefully. And at its core, this is what it says. The stuff at the top here should be familiar from some of the slides that I just went through. This idea of a catchment having a catchment realization that is a flow path. And down at the bottom, a hydrolocation, which could have a reference position, which is an indirect position. The indirect position has some linear element. And so what Mainstems is saying is that the linear element for an indirect position should be a mainstem. And that mainstem should associate to some drainage basin, which is a type of catchment. And what this gives us is kind of a minimally sufficient set of flow paths, which are complete mainstem rivers from headwater to outlet, and drainage basins to cover the landscape at multiple scales to reference our hydrolocation information to. So that's really the key of it. That's the core of it. That's basically that's basically it. So coming back to this diagram, thinking about mainstems for a second, and so let's think about the multiscale nuance here. There's a complete drainage basin with one mainstem flow path. We can represent the incremental catchments along that mainstem flow path, and then add the main stems that are actually tributaries to the first one, where each of those catchments basically breaks up the network, and then add a drainage basin boundary for each of those tributary main stems. And then we could do that again and again and again until we run out of recognizable geomorphic features, right? And if we identify these complete headwater to outlet paths in our data sets consistently, we, at least for the ones that are geomorphically kind of ingrained in the landscape and recognizable as such, we end up with a minimal set of as persistent as possible features. Okay, so some nuances, and the Mainstems paper gets into some of these in in the annexes where we move them. If we try to integrate 12-digit hydrologic unit code watersheds and NHDPlus version 2, this is medium resolution 1 to 100K hydrographic feature lines, we end up with situations like this where there's a flow line that will just tag into the bottom of some catchment or some hydrologic unit and then flow out. So the big black line is saying, okay, the topology of the hydrologic units, which are just boundaries, is saying that things flow this way. The topology of the river network is saying that there's actually some flow that goes into this guy and then out. We can gloss over this geospatial kind of just tagging in and leaving by saying this flow line goes to this main stem, right? And this hydrologic unit is part of this main stem, and move on, right? We don't need to worry so much about that the minutia of how the confluences relate to each other. We can do the same thing at a different scale. So here's zoomed way out, and we're looking at HUC 1002, the Missouri headwaters, NHDPlus version 2, is the blue lines at the 1 to 100K scale, and NHDPlus high res in red. And so we're kind of animating in these pairings of medium res. So the medium res is all there to begin with. And what we're animating in is the matching high resolution features that go along with those. And so this is just done by basically doing some spatial matching between upstream locations of features and how their path traces in the downstream direction. Doing this exercise actually just uncovered the mess that the small features in the 24K NHD geometry has. And it's been a very valuable quality control tool. And at the high level, at the abstract kind of big river level, it is providing a tool to interoperate between these data sets. We can do the same thing with other networks. So we've done the same thing with the old RF1, the river reach file number 1, which kind of almost predates digital representation of rivers, where we can conflate NHDPlus version 2, RF1, and watershed boundary data set hydrologic units into these paths, right? That kind of join headwater to outlet, main stem to main stem. And this brings up a really key question. So I'm kind of wrapping up now. And this is work that is super duper abstract and possibly not worth worrying about too much, but it's interesting to think about. When we say a headwater, what do we mean? Where is the headwater? It's completely scale dependent. It's completely dependent on what you chose as the dominant path. And that's arbitrary. It's dependent on current hydrologic regime. It's dependent on geology. It's dependent on historical, use of the water body and et cetera, right? So what we're looking at right now in red is what the river representation is in RF1. In blue is what the river representation is in medium res NHD. And in black is the river representation in the 24K high res NHD. And there's no one right answer, right? These all have different distinctions of what is upstream main stem. And the ambiguity factor goes up drastically as you get closer and closer to the top of a network, right? But they all converge at some point and then become pretty much unified in their concept of what downstream main stem is. And so what we want to identify is the stuff that we can say is a unified main stem path, right? And be very clear that upstream of this location where everything kind of comes together, we're less certain, and that's just the way it is, right? That's an engineering problem at that point. We need to solve that problem, and we need to push the recognized main stem path further upstream, but that can happen over time, right? As long as we track these things and don't kind of get overzealous. So some future work. In the concept space, I didn't talk about this in detail, but we need some in the kind of elevation derived hydrography, NHDPlus space. We need some core defensible logic for headwater catchments. These catchments that don't have a flow line. And this is actually interesting, slightly aside, but an interesting logical error in a lot of our digital hydrography is that we create a catchment around a first order stream, but we don't create a catchment upstream of the top of the first order flow line. But there is some area that contributes to that initiation of flow, that point where flow initiates in the blue line. There is a catchment upstream of that, and it's akin to the catchment that contributes to the shore of a lake. And we have it both ways, and it's a logical discontinuity in the data sets that puts us in a very tricky situation, because there's some catchments that are on the shore of a water body that work one way, and then headwater catchments that work a different way. And it, from a modeling and a hydrology perspective, it kind of leads us to need to throw away those first order flow lines, because we can't use them the same way that we use everything else. And anyways, it's an aside digression, but it's an important nuance for us to figure out, this zero order catchment issue, and where should a blue line start? Why? What's the nature of the hydrology and the hydrologic system upstream of the initiation of a blue line? It goes, waters of the US rules that EPA needs to think about, all these kinds of things hinge on these kinds of distinctions. And then the second one is associated with this is, what's the relationship between catchment features and water bodies that need to break up the catchment network, right? So at some scale, Lake Winnebago in Wisconsin, for example, should not be part of the network of catchments. It should be a water body that stands out from the network. The Great Lakes, they need to stand out from the network. They need to break up our network of landscape features. So some people call this the dragon's back problem. At what scale and why and how do we break up the coverage of hydrologic units, and say all the little areas that drain to that water body are zero order catchments, right? How do we reconcile this problem across scale? Becomes a very difficult issue. And it's the across scale. At one scale, it's not that big a deal. It's across scale where it becomes very difficult. Okay, so that's all conceptual stuff, hydroscience stuff, hydroinformatics stuff. Technology is another kettle of fish, so to speak. And this gets into social engineering of these kind of cyber systems, these cyber infrastructure arrangements that we make across organizations. So one of the big ones is kind of, what is the minimally sufficient useful and adoptable content for associating hydrologic locations to flow paths, right? We've got all these organizations that collect data across the landscape. They hold some information, they hold different information. Some of it's useful, some of it's reasonable to put out in terms of, adoptability of these approaches. What does that look like? How do we formalize that and specify that content for linking these data sets together? There's work going on in the Internet of Water space on that right now, but it's far from a solved problem. There's a lot of work to do in that space. And the next one, I colloquially refer to this as the network problem. How should large collections of hydrologic locations be handled for linked data? So this is like when you have 1 million model outlet locations, nobody's going to crawl those on the internet. You need to be able to express those as a collection that can be searched and filtered in some way. How do we want to handle that when in reality, all those features are connected to each other in some way and need to be cross-linked to other data sets in an open way? This is a really big issue, and it's something we're really just starting to crack the nut of. And going back to, I mentioned the network linked data index as a tool for discovery. We need more of those kinds of systems that can open up the internals of these massive data sets and provide hooks that allow you to integrate with them and index them, search them, but do it in a way that doesn't create a walled garden, that doesn't create a kind of opaque interface to something that is otherwise inaccessible. So that's what I've got for you. That looks like we've only got a few minutes left. If you have questions, please feel free to follow up with me via email, or look me up on GitHub. I've got a number of projects in this space. I guess I see that one of these DOIs didn't work. Hopefully we can Google and find those and get them for people. But I'll stop there and see if there's any pressing questions in the last few minutes here.
Thank you, Dave. I think we can squeeze in a couple of questions here. The first question is, when you mention drainage in the hydrological system, how do you deal with groundwater? How do you deal with surface groundwater interaction? And what data from USGS may help on this topic?
Big question. So another body of future work is nailing down some of the core concepts of surface water groundwater interactions. We have two disciplines, surface water and groundwater, that have historically not done a great job of talking about the interface between the two, and it's something that we have some work to do on. That said, the core kind of surface water concepts hold, even though some rivers lose, some rivers gain. There's some karst topography where surface water hydrology concepts break down. We just kind of have to avoid those places. There's no answer necessarily to those problems, but the basic concepts of surface water hydrology hold for most of the landscape, and we can kind of lean on that for now, recognizing that a good conceptual basis for connecting the two domains of science does not really exist yet. So,
okay, next will be, is it conceivable in the future to bring the atmosphere into this conceptualization and its role in the quote unquote flow of moisture and substances?
There was actually in high features, there was a recognition of atmospheric interaction with catchment areas in early iterations of the conceptual model. And we really wanted to just scale it back to some of the core pieces of surface water hydrology. It's there. It's absolutely there to be worked on. The idea that a catchment area receives fluxes from an atmospheric or passes fluxes to an atmospheric component of the ecosphere, or whatever the environment, is there to be used, but it's not formalized in the data model right now. So,
I think the next question is sort of answered when you talked about the first one. We have another question in the chat. What efforts are currently being undertaken for broken flow lines due to man-made structures such as culverts, and how accurate they are?
This is a big issue, and it's one that we are going to be working on forever, probably. The stuff that I'm talking about here is intended to be at a scale where those kinds of issues don't present themselves. But the techniques that I was talking about here, and like I was talking about how, the conflation of NHDPlus medium resolution to high resolution really just uncovered more issues in high resolution than it solved, to conflate the two data sets. It was a quality control step on exactly that, right? If you find that you drop a virtual raindrop at a headwater and it stops and doesn't go where you expect it to, well, you maybe just found a place where you need to make a connection. And whether that's a geometric connection or a topological connection is something you can kind of take up in however you're working on it. But yeah, that becomes a huge issue. And hopefully as we work forward, we can increase the density with which we know these connections from headwater source areas to outlets. And that can become kind of a basis for quality control of future data. That's the vision anyways. So.
We don't have any question right now. I think we are slightly out of time. Very nice talk, David, and it was really a very interesting presentation. Julia, you want to come in? Okay.
I think we're done here. Thank you so much for coming,
Thank
everybody.
you. Thank you so much, David, for the wonderful talk. Thank
Yeah.
you so much. Yep.
Yeah, absolutely.
Yeah. Thank you. Bye-bye.